Okay, we have here another integral on the board, and we want to find a general solution for the integral from minus a to a of h of x over 1 plus b to the g of x dx. And we have this defined over here to the right, where this h of x in the numerator is going to be an even function, and this g of x is going to be an odd function. This b is just some number, and the same thing with this a, this will be some finite number. And just to make it a little more clear, I could kind of come up with some example for this. So like, for our a, let's say we're integrating from minus 3 to 3, and we need an even function for h of x. So let's say I can make that x squared, and then we could have 1 plus, for our constant value, our b, we could do this like e to the, let's say, sine x as our odd function. So this would be in the same form as what we have right here. So the way I'm going to do this is by substitution. So I'm going to make a u substitution for minus x. So of course, x is minus u, and our dx value is minus du. So we'll go ahead with this substitution. It's just going to change the sign on our bound. So now we're going from a to minus a. For our h of x, this is going to become h to the minus u, h of minus u, 1 plus b g minus u minus du. Now what I can do with the minus sign, we'll use that to flip the bounds. So now we're back to going from minus a to a. And this is where the even and odd functions come in, right? Because again, h is an even function, and so the definition of an even function, that's just going to change this minus sign to a plus. And for an odd function, we can take the minus sign and bring it out front. So what I could do from here to transform this, I'm actually trying to get my denominator to look like this. And so to do that, I will just multiply numerator and denominator by b to the g of u. This is just multiplying by 1. So when we do this, let's see what we have. Now when you multiply this into the denominator, multiplying the b to the gu to the b minus u, the exponent's going to become 0, and we just get a 1. And then multiplying into the 1, we just get this term back. But from here, what I'll do is a variable change. I want to change it back to x because I'm trying to add it to our original integral. I'm just going to call this original integral I. So let's just do that variable change. Okay, so now that we have this back to x, I'm also going to label this integral I. We'll add this one and this one. So this is going to give me 2 copies, or 2i. And then when we do that, because we have the same denominator, we can just add the numerators. So we end up with h of x plus h of x bg of x over this common denominator. But then the key to this right here, what I can do is factor out an h of x. So what's going to happen when we factor that out, I can write this as h of x times 1 plus b g of x. But then this thing's going to cancel, and we get some good simplification. And now we're just integrating h of x. But the nice thing here about integrating h of x, with h of x being an even function, we have this property. If we integrate an even function with symmetric bounds, what we can do is we can change the lower bound to 0 and bring a 2 out front. And so that's what we're going to do right here. We'll write this as a 0, and we'll bring a 2 out front of the integral. But then I can just cancel a 2 on both sides. And so what we've done is we've reduced this, and we're saying the solution for our integral, we're just going to need to integrate from 0 to a of h of x dx. So of course that's not much of a solution, but the way these things usually work, h of x is usually something easy, like let's say it's x squared, or let's say it's cosine of x or cos of x. Well, then you have a really easy integral and you're basically done. So that's it, just going over the general form of this integral. We'll stop it there. Thanks everyone for watching. Have a great day.